Assalamu alaikum, dear students. If you remember in the previous lesson, we were talking about waves in general. We said we have transverse waves and longitudinal waves. And of course, we made the difference between them. And we emphasized, for example, the role of each when it comes to wave or particle vibrations. We said in transverse waves, basically the particles would vibrate back, let's say up and down, or you can say at a right angle perpendicular to the direction of wave travel. While on the other hand, to longitudinal waves, the particles were moving parallel or vibrating parallel to the direction of wave travel. And then of course after that we were talking about the types of, let's say, wave interference, constructive and destructive interference, and of course all the other concepts that we went through, and of course including the questions and the examples that we've solved together. All right, today we'll go through a new unit, of course, and that is Unit 4, Chapter 4, you can say. But remember this: we're still talking about sound, so of course there is a huge relation between the two. So it's very important to make sure that if you didn't understand all the concepts that we went through in Unit 3, now you pay attention, or at least you go back to those concepts and then make sure you revise them and you understand them before going through with this one. All right, so today we'll talk about sound here, okay? So of course that is Chapter 4. We're going to study the physical aspects of sound, of course, including the nature of sound waves, frequencies, intensities, resonance, and harmonics as well. And of course, we'll go through sound waves, we'll go through the sound intensity and resonance as well, and then we'll end up with harmonics that we will go through, inshallah. All right, so the first thing to begin with is basically 4.1, and that is sound waves. We did talk about sound waves in the previous unit. We said basically normally sounds are caused by vibration, yeah? So how do you describe or how do you define a sound wave? You can say sound wave is a longitudinal wave, and of course it is traveling, or you can say longitudinal wave that transmits sound energy through a given medium, or you can say, or through a medium, by what? By vibrating the particles, or by causing the particles to vibrate. Once again, you can say sound wave, it is a longitudinal wave, okay? Its job is to transmit sound energy, or the energy of sound. And how does it do that? It does transmit the sound in a given medium, so there must be a medium. And how does it do that? By making the particle of the medium vibrate. Okay, so basically this is longitudinal wave, for which basically we can say sound wave in this case, because we're talking about sound waves. So remember this: the cause of every sound or every wave, of course, it is a vibration. Yeah. So without a vibration, you will not have any wave in terms of sound energy. Okay. And of course, now let's say we have this tuning fork. What happens when you struck the tuning fork? And of course, when you strike the tuning forks here, of course, this tuning fork will vibrate. Yeah. This vibration will cause the air that is, or the air surrounding or nearby, let's say, to vibrate. And of course this vibration will pass through, let's say, the given medium, which would be the air in this case here. But remember this: when these vibrations are passing, for example, through the sound particles, it creates a series of regions, let's say. And of course, what did we call those regions? We call them compressions and rarefactions, if you remember. So compressions and rarefactions basically are regions where or you can say regions where some regions where the air particles are compressed or very close to one another. That is compression, of course. And then we have rarefaction, which basically the air particles are far away from one another. Or you can say the pressure and the density will be less compared to there. So we can represent the sound wave by many examples. Let's say we have a speaker, starting with a speaker, or we could have, let's say, a tuning fork, which in this case, they both cause vibrations. Okay, so, and of course there are air close to the surrounding here. So when the speaker vibrates, it moves, the cone of the speaker moves back and forth. Or if it is a tuning fork, the tuning fork, let's say, or the prongs here, would move back and forth, back and forth. This back and forth, of course, creates regions where the air particles are, let's say, close to one another. Okay, there's a region where the air particles are very close to one another. And of course, we have other regions where the air particles are far from one another. Okay, once again, we have another region where the air particles are very close to one another. Okay, and then of course other regions where the air particles are far from one another. So if not, we can represent this by using lines where the air particles are very close to one another, and then the air particles are far from one another, and then once again the air particles are close to one another again, and then far from one another as well. Okay, so let's go back to this. The air particles are far, not this, the air particles are far from one another. So you can see this one here, we can use or represent this using a spring. Of course, we did use this one as well. We said there are some regions, if we use a coil of spring, of course, some regions you see that the air particles are close to one another, and some other particles or some other regions where the air particles are far from one another, okay, like this. And of course, here would be this. Now, and of course, we said we can represent this using a sine wave as well. We said those regions where the air particles are close to one another, we can represent this by using what? By using by drawing a crust in here, okay? So for example, if I have a sound wave, I would be drawing this. Not this, let me do this one more precisely. We can say this is a crust and this is a trough, another crust. You can see here, it's not very precise, but something like this. So you can see here, those regions where the air particles are close, of course, in these regions, the air particle are very close to one another. We call them compression. And these regions, you can see here, the pressure is maximum. Why the pressure is maximum? As you can see here, the air particles are pressing on one another. There are too many air particles given in a specific, or let's say given in a space. Okay, and the same for the spring or these lines as well. So of course we can represent this region here, compression, as a crust, okay? And then we have here rarefaction, where the air particles are far from one another. And of course in these regions you can see less air particles, so we can say the density and the pressure are less compared to this. And of course we can represent this using the trough if we're going to use a sine wave here. So once again, the region where the air particle is, where the air particles are very close to one another is called compression. The region where the air particles are far from one another is called rarefaction. Very, very good. Or I can change the question. I can say the region where the pressure and the density of the air particles are the highest or the most or maximum, that would be compression. The region where the pressure and the density are minimum, you can call that one rarefaction. So this region here, we can call it what? We can call it compression. Let me write that one down. So we call this one compression. All right. And of course, this region where the air particles are far from one another, you can call it rarefaction. All right, so now you tell me what is the difference between compression and rarefaction, yes? So compression is a region where the air particles are very close, where the pressure and density is the highest. Rarefaction is the region where the air particles are far from one another, or the pressure and density are the minimum or the least, you can say. Very good. So take a look here. Sounds are always caused by vibration. Without a source of vibration, you can never have a sound. Very good. And as you can see here, when this vibrating, or let's say tuning fork prongs vibrate, of course, it causes regions where, you can see here, we have different regions. Regions where the air particles are far from one another, and then regions where the air particles are compressed, or too many air particles, and of course we have this. We can draw this, or we can say, this region where the air particles are the most, or the pressure is the highest, that will represent the crust of a sine wave, let's say, and then the other region where the air particles are the least, the maximum, or the pressure and the density are the least, we can say minimum, the least, that would represent a trough here. How do we get this? Take a look. When these tuning fork, you can say, or these vibrations, you can say, here's normally what it is. When there are air surrounding this, so when this one vibrates back and forth, of course, when it, let's say, vibrates to the right, it pushes all the air particles, or, for example, to the right. And of course, you can see here the air particles are compressed here. Okay? And then what happens when it, let's say, after it goes forth, now it goes backward, yeah? Back and forth, let's say. So this one here creates a region where there are less compression, less air particles, and of course, this one would produce what? Produce a, let's say, rarefaction, and this would be a compression. So once again, the resultant of this is going to be something like this. So this is basically what is a sound wave, or creates a sound wave, basically, this vibration. So as you can see here, the information, it tells you all about what we have just explained. Now we have two definitions here, compression. So after we know what is compression, or after we went through compression, how you can define compression, we can say compression is a region of longitudinal, or a region of a longitudinal wave where the pressure and density is at maximum, you can say. Now we have rarefaction. That would be the exact opposite of this, a region of a longitudinal wave where the pressure and density would be minimum. Very, very good. Now we have a question here, says sound waves are longitudinal wave. Do you remember we covered transverse and longitudinal? Why sound wave is considered, or why sound wave is longitudinal? Well, very simple. Now, first of all, think about the vibration of the air particles and how do they vibrate when the sound is, let's say, transmitted through a given medium. Or do, let's say, the particles of a, let's say, medium, do they vibrate perpendicular to the direction of wave travel, or do they vibrate parallel to the direction of wave travel? Excellent. So because the vibrating particles in a sound wave, let's say, move parallel to the direction of wave travel, so of course that is why we call it longitudinal wave. So we can say, because the vibration of the air molecules are parallel to the direction of wave travel, and this is why we call this longitudinal wave. The simplest longitudinal wave produced by a vibrating object can be represented by a sine wave. We did talk about this one. So we said that this is basically a region of high pressure and density, that is basically compression, rarefaction, compression, rarefaction. We can represent each one of these compressions as a crest of a sine wave, let's say, and each one of these rarefaction as the trough of a sine wave. So of course you can see here, this would be basically simultaneous of this, or you can say this compression corresponds to the crest of a sine wave, and of course you can see the rest as well. Okay, but remember this, there's one thing you need to know. When we talk about a sound wave and you have the amplitude like this, or the sine wave, you can see here the amplitude never decreases. Now here we have an idealized situation, otherwise the sound cannot continue traveling or spreading through the medium forever. You do know that sound wave is an energy, and of course this energy will disperse in the or within the environment here, so of course this energy will be dissipated. So but what you see here, and of course energy is related to the amplitude, yeah, so you can see that the amplitude doesn't decrease because we're idealizing this situation. Otherwise you would see that eventually this amplitude of the sound wave, you can see here, it would start to become less and less and less until it eventually kind of like touches the horizontal form where there is no sound at all. But why it doesn't happen here? Because we're idealizing this case here where we assume that there is no energy wasted. But we do know that in reality, the energy is wasted, or there is energy loss. Now, the characteristics of sound waves, remember this. Sound waves are characterized, of course, by the frequencies that they have, of course, all right? And this is, for example, now the frequency of my sound is basically different than yours, yeah? And of course, yours is different than your friends, and your friends is different than someone else, let's say. So what characterizes sound, of course, the frequency, yeah? Basically, frequency, that would be the identity of a sound, let's say. And this is what makes my sound to be different than yours. So we have three types of sound, basically, here, okay? What are these three types of sound? The first one is audible sound, all right? These audible sounds are basically our sound that we can hear them. This is why it's called audible sound, because it is audible that humans can hear, basically. Now we have another type of sound which is called infrasonic sound. Infrasonic sounds, of course, are those sounds that we don't hear them, and of course, but they have a very low frequency, let's say. And then we have another type of sound which is called ultrasonic sound, and that is, these are basically ultrasonic waves, or those are sounds that we do not hear them. That is because of their high frequencies. Now let's talk about this one a little bit more. So what is audible sound? Audible sound is, or audible waves, let's say, are those sounds basically that humans can hear them, and their frequency range between 20 hertz to 20,000 hertz. Remember this. So once again, audible sound waves are those waves that their frequencies range between 20 hertz to 20,000 hertz. If I don't want to say 20,000, I would say 20 kilohertz, because you do know that kilo stands for 1,000 here. Okay, that is basically audible sound, yeah? And of course we have infrasonic sounds. Remember, infrasonic sounds are those sounds that have frequencies less than 20 hertz. Remember, we said humans can hear sounds of, let's say, frequencies of 20 to 20,000, yeah? So those sounds that are below 20 hertz, let's say, we call them infrasonic sounds or waves, you can say. All right, and then we have ultrasonic waves, yeah? Ultrasonic waves are those waves or those sounds, of course, that have a very high frequency, and humans do not hear them. Why? Because it is out of the range of human hearing, let's say. Okay, so of course, ultrasonic waves are those waves that human do not hear, and the frequencies basically are from 20,000 hertz and above. So any frequency higher than, let's say, 20,000 hertz will not be heard by humans. All right, now we can categorize this. Remember that. Now we do know that. Let's just organize this as it is. Let's say we have audible, right? Or I can start with ultrasonic, let's say. Ultrasonic, right? And then we have audible, and then we have infrasonic waves, let's say. Now, in terms of frequency, let's say, of course, we said the frequency of ultrasonic waves are bigger than what? And bigger than the frequency of audible range, all right? And of course, the frequency of audible, let's say, is bigger than the frequency of the infrasonic. But hey, remember this. Now, the speed of each one of these sounds in a given medium at a certain condition, these are all equal. Don't forget. So that means the speed of ultrasound is the same as the speed of audible, which is the same as the speed of infrasonic, given the same medium. Let's say same medium as air, let's say at a certain temperature, let's say at 25 degrees Celsius, let's just say, assume. All right, then each one of these would have the same speed here. So remember this, we can say the speed of this, and of course we can say, let's just say the speed of this equal to, that is for ultrasonic, which is the same as the speed of audible, which is the speed of, let's say, the speed of the sound for infrasonic. But you do know that frequency and wavelength are inversely proportional. And what does that mean? That means if a sound has a high frequency, it must have a short wavelength, yes? So in another word, we can say the wavelength of ultrasonic has to be the least compared to the other one, which is going to be smaller than the wavelength of audible, right? Which is going to be smaller than the wavelength of the infrasonic, all right? Infrasonic waves. But in terms of their speed, these are all equal. And remember this, whenever questions come in Wizari, let's say, or national exam questions, you can always do this, just to remember this, and then of course any question related to this, you'll be able to answer them very easily. Just remember this. This one is the highest frequency, which is 20,000 and above. This one, audible, is between 20 to 20,000, and this is below 20. So, of course, the highest frequency, right, and this is the lowest frequency. If the frequency is the highest, then the wavelength must be the shortest, all right? And then, of course, so the wavelength of this, because they all have the same speed, yes? So if the frequency is very high, then of course the wavelength must be short in order to have the same speed of sound in a given medium, yes? And here, of course, you can say the frequency is lower than ultrasound and then ultrasonic, let's say, but the wavelength is longer because the frequency is less, so that it can have the same speed. What about this one here? This one has the least frequency. If it has the least frequency, then of course it must, let's say, have the highest or the longest wavelength so that we can have the same speed as well. So remember this. This is how you can remember, just remember the organization here. And then any question related to this, of course, you will be able to answer them without a doubt, inshallah. So these are basically what we have for audible sound waves, for infrasonic waves, and of course for ultrasonic waves as well. So going through this a little bit more, we can say sound waves are basically that the average human can hear, have frequencies ranging between 20 hertz to 20,000, or you can say 20 kilo if you don't want to write, once again, if you don't want to say 1,000, of course you can just say 20 kilohertz in this case, okay? Very good. Infrasonic or sound waves with frequencies less than 20 hertz, and of course you can say elephants can make and hear these sort of sounds here. Ultrasonic waves or sound waves with frequencies higher than 20,000 can be heard by some animals like dogs and horses, and of course can be used to produce images of objects inside the body like fetus, for example, or kidney stones, let's say. Bats use ultrasonic waves for echolocation here. Okay, and of course you can see this one. Always remember this arrangement here. Each one of these, let's say, sound waves would have the same frequency in a given medium. Let's say if the condition is the same for all, but their frequencies and wavelength will be different, of course. Okay, now we have another question here. It says, what are the frequencies, or what are the differences between infrasonic, audible, and ultrasonic sound waves? We said their frequencies, remember, are different, or their frequencies, what makes them to be different, yes? Remember, these all have the same speed, so that is not a difference, yeah? So, but we can say infrasonic sound waves basically below 20 hertz, audible range between 20 to 20,000, and ultrasonic waves are basically from 20,000 and above, you can say. But if we can compare or contrast the wavelength, of course, we can say the wavelength of infrasonic, if it has the lowest frequency, so the wavelength must be the longest. This one is in between, and of course the wavelength of ultrasonic would be the shortest compared to the other two. All right, now, remember we have a study tip. It says, an individual's hearing depends on a variety of factors, including their age, all right, and of course, experiences with loud noises. Now, do you know that we as human, when we grow up, you know, like the structure of our ears will be different, of course, or you can say maybe some parts of our ear will get a little bit stiffer. That's one thing. Another reason is maybe some of the cells, or basically those cells that are responsible for, let's say, vibration and transmitting the sound, some of them will be damaged, some of them will die out, let's say. So of course, our ability to hear sounds with higher frequencies will go lower. In another word, that as we grow older, our hearing ability will be less and less and less. You might say, Mr., but if that is the case, then why do we say from 20,000 to 20,000, okay? Even though, for example, for someone like, let's say, a mature person, somebody who's in, let's say, 25 or 30, their hearing ability might be about 14 to 16,000 hertz, let's say, or 1,000 hertz, of course, or kilohertz, right? But why are we still saying 20,000? That is because that is the range for human. It could be for a toddler, let's say, up to for someone who is in a good condition. But normally, as we grow older, as we go in age, of course, our ability will get lower and lower, or in other words, we don't hear frequencies that are very high. All right, in the range of hearing, by the way. Okay, so experiences with loud noises. You would see that, for example, these people, or the musician here, once they are, or you might often see them, they are, or there is something basically inside their ears, protecting their ears, because even though the sound of these instruments might seem very nice, but at the same time, if you're hearing them for too long, it might be very annoying. It might damage your, let's say, your hearing, okay? And of course, you have to protect them. And if you're, let's say, if you see workers, sometimes they use ear shielding, right? And of course, this ear shielding would protect the ears so that they don't get, their hearing system won't get damaged, let's say, very soon, yeah? Or of course, if they don't, if they are experiencing noise for too long, of course, this noise would affect them and reduces their ability of hearing. So it's very important to protect your ears. All types of sounds, remember this, all types of sound, whether if it is audible, whether if it is infrasonic or ultrasound, these all have the same speed, you can say, in a given medium. And of course, all of them, remember this, all of them need a medium, particles, so that they can transmit the disturbance, the sound energy, or just the energy, you can say. Okay, and the reason, and this is basically another reason why we call these sound waves longitudinal waves, yeah? Okay, because, or not longitudinal, mechanical waves, because they do need a medium. Okay, so remember this, and all of these sounds need a medium to travel through. They cannot travel through empty space. But remember, electromagnetic waves like light waves, let's say, or laser light, or any other electromagnetic, could be radio, could be infrared, could be microwaves. These do not need a medium. But sound waves, all of them need a medium. Why do ultrasound waves produce an image of objects inside the body, let's say, more effectively than audible sounds? And of course, That is because ultrasonic waves are basically have higher frequency. That means you can say they can penetrate through the body more effectively, and of course then they would be reflected, and of course this would provide a higher resolution or image, or you can say a clear image. Okay? Alright, now we have some national or WSAT exams, yeah? Of course, past ones. Take a look at these. The first one says the region of longitudinal wave in which the density and pressure are at minimum. Remember, we said there are two regions basically. Regions where the pressure and intensity, let's say, not intensity, my bad, density, right? Pressure and density are at maximum, that we call compression. And then the other region where the pressure and density are minimum, that is basically rarefaction. So remember this is for longitudinal wave, yeah? So in this case we can say, remember, we have a longitudinal wave in which the density and pressure are at minimum. If it is at minimum, that is obviously rarefaction. Look at the second question here, the same question, but except then the end of the question is different. It says where the pressure is at maximum. The pressure, longitudinal wave, a region on a longitudinal wave where the pressure is at maximum, that is clearly compression. Remember, trough and crest, these are for transverse wave, which that is not the case here. We just have compression and rarefaction for longitudinal, and then which one of them is where the pressure at maximum? That is obviously, it is compression. Now we have question 3, says the frequency of a sound wave heard by the average human range, that is, or ranges from what we said, the audible range, or the frequencies that human can hear are basically range from 20 hertz to 20,000 hertz. And sometimes, of course, instead of this 20,000, you might be given 20 kilohertz as well. That is also the same thing. So 20,000 or 20 kilohertz would be the same thing in this case, and you should know them. Now for question 4, I would like to make a pause in here because this is something very important. And of course, I told you this could be a little bit confusing, yes? But of course, if you're following my instruction, inshallah, you will do these questions easily without making any mistakes. So how do we do these? Stay with me. Take a look here. It says, which of the following is not true for audible, infrasonic, and ultrasonic waves in the same medium? So we have a condition. These are all in the same medium. We said that before, let's say, we did talk about, so we said ultrasonic, yeah? So ultrasonic, and of course we have audible, all right? And of course we have infra, yeah? So if we compare the frequencies, we said the frequency of ultra is bigger than the frequency of audible, which is bigger than the frequency of the infra, yeah? But because the frequency is the highest, so the wavelength must be the lowest, all right? So the wavelength of ultrasonic wave is smaller than the wavelength of audible, which is smaller than the wavelength of infra. So we can say the wavelength of infra is maximum, all right, while the frequency is minimum here, all right? But on the other hand, you can say the frequency is max and the wavelength of this is minimum, you can say, all right? So, and what about their speed? Their speed is all the same. Why? Because these are all in the same medium, you can say. And these are basically all sound, so they have the same speed. So now, take a look at the first one here. It says the wavelength of, the first one says the wavelength of ultrasonic is bigger than audible range, yeah? The wavelength, by the way, it says which one is not true, yeah? So this one, the first one says, by the way, the question is not about the frequency, so you don't have to look at this part here. But if it was about frequency, then of course you would have to look at this one too. So it's about the wavelength, so we compare their wavelength. The first one says the wavelength of ultrasonic, this is ultrasonic, yeah? It says it is bigger than the wavelength of audible. Is the wavelength of this bigger than the wavelength of audible? The answer is no. So this one is the incorrect answer, but you have to look at the other options as well, right? Now this one says the wavelength of infrasonic is bigger than audible, right? Where's the wavelength of infrasonic? That is, this is bigger than the audible, so this is correct, right? So we're not going to choose this. All right, what about this one here? It says the wavelength of ultrasonic is smaller than infrasonic, yeah? The wavelength of ultrasonic is smaller than the wavelength of infrasonic. That is also correct because this is minimum and this is maximum, yeah? So of course it is smaller. The other one, the last option, this is not the correct, by the way, I'm just trying to point out this one here. It says the speed of audible is the same as the speed of infrasonic, which is the same as the speed of ultrasonic. And of course this is also correct, so this is not the option that we're looking for here. So the only correct option would be option A in here. So once again, always whenever the question is about these sounds, yeah, or the types of sound, always draw this, all right, diagram for both frequency and wavelength, and even the speed as well, by the way. And then using this would help you very well so that you can make a correct judgment, and then of course choosing the correct answer here. Okay, it says the frequencies of infrasonic. Remember, the frequencies of infrasonic. We have audible, we have ultra, and we have infra. So infra is basically 20 hertz and below, yeah? Very good. Or you can say less than 20 hertz, by the way, not 20 and less. So less than 20. Okay, so of course frequencies of infrasonic wave, that would be less than 20, which is option A here. All right, and then you can see the other options are incorrect. The frequency of ultrasonic waves. Ultrasonic, that was the highest you can say among the three types, yeah? So of course it is more than 20,000 hertz, yeah? You can say more than 20, that is also correct. Less than 20 hertz, now lies between this and 20 to 20,000 hertz, now that is audible. And then lies between 1,000 to 5,000 hertz, that is incorrect as well. So the correct option would be more than. Ultrasonic would be more than 20,000 hertz. Now question 7 says the sound waves with frequencies greater than 20 kilos, see, cannot be heard by human. What is it called? Is it infra? Of course it is not. It is the ultrasonic waves, yeah? All right, now question 8 says which of the following waves are longitudinal waves? Remember, we have infrasonic waves. Infrasonic wave, it is a type of sound wave, and sound is longitudinal. So the correct option is will be option A here. But let's take a look at the other option. What about this one? Ultrasonic. Wait. It says which of the following waves are longitudinal waves? Yeah. So this one, it is a longitudinal wave. What about ultrasonic wave? It is longitudinal. What about audible wave? It is longitudinal wave. So in this case, we'll say all of them are correct in here. What about question 9? It says which of the following waves is a longitudinal wave? All right. X-ray, it is electromagnetic wave. Ultraviolet, that is also, let's say ultraviolet wave is basically is among the visible, yes? No. I mean among the electromagnetic wave here, ultraviolet, that would be UV, right? Ultraviolet, all right? That is UV basically, electromagnetic wave. Sound is a longitudinal wave. What about infrared wave? That is also electromagnetic wave. Incorrect. So the correct option will be or is sound waves in here. Okay, now we have a new concept which is basically says frequency determines the pitch. Okay, now what is a pitch? Basically tells you pitch is a measure of how high or low the sound of a wave is per, let's say the sound or sound is perceived. Let's say how high or low, let's say the frequency of the sound that is observed, that is heard, let's say. If you observe a sound that has a very high frequency, of course we say that sound has a high pitch. What if it is a sound that has, for example, a low frequency? Then we say this sound has a low pitch, let's say. So high and basically high, whether pitch is high or low, it depends on its frequency. Normally, or the pitch of a sound, let's say the sound of men basically has a low pitch, so you can see it's a little bit, what do you say? It is not that sharp compared to the sound of, let's say, females in general, yeah? The sound of females normally have a higher pitch or higher frequency, you can say, right? So we can say pitch is a measure of how high or low a sound is, let's say, preserved to be or perceived to be, like how much the way that a sound is heard, you can say, perceived, yeah? All right, to be depending on the frequency of a sound wave. Does the pitch, or what does the pitch of a sound depends on? Remember, there are three factors that the pitch of a sound depends on. What are these three factors? The first one, we said the pitch depends on a frequency. The higher the frequency, the higher the pitch. And of course, the lower the frequency, the lower the pitch. That is one. Second thing is, it depends on the background noise. And of course, when there is a lot of noise, let's say in the surrounding area, if you're talking, maybe your sound, of course, will be mixed with theirs, so you cannot hear that sound very well. Yeah. So how can you hear a sound in a very noisy area, let's say, or environment? Then in this case, you'll have to, let's say, speak louder, let's say, or use a sound that is at a very high frequency, let's say, as long as it is in the audible range. And then, of course, the loudness as well. So the third factor that the pitch depends on is the loudness, yeah? So once again, what does the pitch, let's say, depends on? It depends on the frequency, it depends on the background noise, and also depends on the loudness as well. The pitch increases by increasing the frequency of a sound. We've mentioned that. Now we have question 4 says, what is the difference between frequency and pitch? If you remember in Unit 3, we did talk about frequency, yeah? So basically frequency is the number of vibrations per unit time, you can say, or the number of cycles, like how many times does it vibrate in 1 second, let's say. That is frequency. But pitch, you can say, is basically how high or low the sound is. You can say refers to the perceived frequency of a sound wave by a listener, and it is subjective. You can say, what does it mean if it is, let's say, subjective? Of course, it depends on the listener. That means I might hear frequency, you might not hear, or we might not hear the same frequency. And that is, if you remember, we said there are different factors that affects our let's say, hearing ability. Yeah, maybe if you're somebody who have a good condition of, let's say, hearing, of course you can hear all the frequencies or sounds at their exact frequency. Yeah, but if it is somebody who has troubles with, let's say, the hearing ability, of course maybe they are not able, or they might not be able to hear all the frequencies, or the frequencies at a certain range, let's say. So the pitch of a sound, you can say it is subjective. It is different from one person, let's say, to another. But once again, so what is the difference between the two? One more time. Frequency is the number of vibrations per unit time, while pitch, it refers to the preserved, let's say, or perceived, let's say, frequency, like how high or low the frequency that is received by the listener. Okay, this one we're not covering that because it is not included anymore. Now let's talk about the speed of a sound. Yes, what is the speed of a sound? We do know that the speed of a sound, and of course we covered this one as well previously, that speed of a sound is basically equal to what? Speed of a sound, we can say, okay, I think, yes. Let's, all right, speed of a sound, we do know that we have this equation, yeah? Wavelength equal to frequency times the wavelength. And of course we said, given the same medium and the same condition, of course, the speed of a sound in the same medium will always be the same, yeah? If it is, for example, air, the speed of sound in the air will be the same for all the sounds, regardless to the frequency or their wavelength, let's say. So if a sound has a very high frequency, of course, then their wavelength will be very short, and of course it's vice versa. If the frequency is very low, then their wavelength will be long, yeah? Very, very good. But what happens, let's say, when we change the medium, of course? Now things will change, of course. We do know that the speed of sound is different in different medium. And guess what? The speed of sound is the fastest in solids, and then after that it is in liquid, you can say, and it is slowest in, and then of course it slows down in liquid, all right? And of course it is the slowest in gases. You might wonder how. That is because, remember, the solid particles are very close to one another, yeah? So sound waves, you can say, will transfer the energy very quickly from one particle to the other. Then the one particle will give the energy, the disturbance to the neighboring particle, and because they are very quick or very close, so they can transfer the energy very quickly from one particle to another, and then this is how they can transfer the sound very quickly in solids, which is about, let's say, in solids about 5,100 meters per second. In liquid it is about 1,500 meters per second, but in gas it's about 340 meters per second, you can say. So of course you can see there's a huge difference between the two. Why the sound, you might be asked, why the sound is the slowest in gases? That is because the gas particles are very far, yeah? So of course when one particle has the energy, it takes, let's say, time for this particle to give all this energy to the neighboring particle because they are far, obviously. So of course this will take a lot of time, so which slows the speed of sound in air. So remember this, the speed of sound in solid is the greatest, is the biggest. Then after that it comes, let's say, slowest in, slower in liquid, and it is the slowest in gases. And of course you can see this table here, or before that we have a question that says, what does the speed of a sound depends on? You can see that it depends on two factors. Depends on the speed of sound, depends on how quickly one particle can transfer its energy, the disturbance or the motion, let's say, to the neighboring particle. Let's say that is one. Second, of course, it is the temperature of the medium. You might say, why the temperature? Because the temperature makes the particle, let's say, once you increase the temperature, the particles start to vibrate faster. So if I have, let's say this, or this hand is basically one particle and has the energy, let's say, the faster the vibration, the more the temperature, the faster the vibration. So the faster I can, assuming that this pen is the energy, the faster that I can, for example, transfer this energy to the other hand, and then this hand to another one. That's how we can transfer the energy, let's say. So in short, the higher the temperature, the faster the vibration, or the more the kinetic energy. The faster the vibration, the more or the faster the energy transfer, basically. All right, that is why temperature affects the speed of a sound. But remember this, okay? Later on you will see we have a question. Once we increase the temperature, of course that increases the speed of sound. And this increase in sound, it is very noticeable in gases, but it is less noticeable in solids and liquids. Why? The reason why is this, because gas particles are very far from one another. Giving a little amount of gas particles, it makes them vibrate a lot. This vibration gives them a lot of kinetic energy. This kinetic energy causes more collision. So more collision, or you can say faster collision. All right, more collision at the same time as well. So this energy can be given to the neighboring particle way quicker. Why it is not the same case in solids or liquid? The reason is this, because solids and liquids are already close to one another. So even when you heat them, let's say to the same degree as, for example, you're heating a gas, now because they are bound very close to one another, so their kinetic energy will be faster. That is true, no doubt about this, yeah? But then because they're already very close, so this closeness or this change in temperature does not affect the speed of the particles, or this, let's say, how fast they transmit the sound that much. So let me make it short. The effect of temperature change is very noticeable, or more noticeable in gases compared to solid and liquids. So that is because the gas particles are very far, giving some thermal energy would make them collide, move faster, more collision, or they can transfer the energy faster. But it is less obvious in solids or liquid because they're already close to one another. So their vibration will increase, but it is not that much compared to what happened in gases. Okay, so that is, of course, what, let's say, the sound transfer depends on, yeah? Or the speed of sound depends on this too. Depends on, let's say, how quickly one particle can transfer its motion to another particle, or you can say the state of the object, all right, whether for a solid, liquid, or gas, and then the temperature of the medium as well. Take a look at these two tables, by the way. You don't have to memorize this. This is just to compare, to help you to see this. The speed of sound in different mediums, of course, you can see. If it is for air at 0, let's say degrees Celsius, it is about 331 meters per second. When you increase the temperature to 25 degrees Celsius, of course, you can see that it becomes about 346, basically. Okay, if it is at 100, it is about 366 let's say meter per second. These are helium or whatever. Look at the other one here. If it is a liquid at 25, it is about 1,140, or seawater, it is about 1,500, let's say. And if it is solid, at aluminum, for example, which is about 5,100 meter per second. And that is pretty fast if you compare it to just 331 meter or 300, even 40 meter per second. Or it could be even, let's say, 1,500 as well. So you can see that the speed of sound in solids is the fastest. Why is the speed of sound as fastest in solid? That is because in solids, the particles are very close to one another, enabling them to transfer their motion, the disturbance, their energy very quickly, or more quickly than in liquids or gases. Now take a look at this question. We were just talking about this, explain why the speed of sound depends on the temperature of the medium, and also why is this temperature dependence is more noticeable in gases compared to solids or liquid. That is because as the temperature rises, the kinetic energy increases, more collision, yeah? So leading to a more frequent collision in gas, you can say. This allows the disturbance, the motion, the energy to propagate faster at a higher temperature, let's say. But in liquids and solids, you can see the particles are close enough together that the difference due to temperature change is less noticeable, all right? As for question 8, it says, if the wavelength of a sound source is reduced by a factor of 2, what happens to the wave's frequency? And of course, what happens to the speed of a wave? Remember, as long as it is in the same medium, the speed never changes. And this is a general information, you need to know this. As long as the medium is still the same medium, and as long as the temperature doesn't change, the speed will always be the same. Whether if it is infrasonic, whether if it is infrasound, let's say, whether if it is audible sound, whether if it is ultrasound, yeah? So the speed is always the same. So if, watch this, let's say, let's do this. Remember, it says, what happens to, what was the case? It says, what happens if the wavelength is reduced by a factor of 2. So speed, we know that equal to frequency times the wavelength. If the wavelength is reduced by a factor of 2, now the speed is the same, yeah? So in order to keep the speed the same, so the frequency will be doubled in this case. Or in another way, you can say frequency, right, and wavelength are inversely proportional. Or what are inversely proportional? So if the wavelength decreases by a factor, let's say of 1/2, then of course this one, if you take the reciprocal, then the frequency of course will be increased by a factor of 2, you can say here. Or just forget this here, you can say if these two are directly or inversely proportional. If the wavelength increases by a factor of, let's say, decreases or becomes half, so 1/2, then the frequency must be doubled, yeah? What if it is the opposite way? What if the frequency becomes half? Then the wavelength will be doubled. Okay. Now the last question for this session is, it says, as a result of a distance explosion, an observer first senses the ground tremor, which is the vibration, yes, the shake, then hears the explosion. What accounts for this time lag? Let's say there is an explosion. Yeah. First of all, you feel the earth. Let's say the shaking, the vibration, right? The shake, and then later on you will hear the sound. Why? That is because, remember, the sound that you hear passes through the air, but the vibration passes through the earth. So can you guess what is the reason why? That is because, or the answer obviously is this, right? The vibration that passes through the earth, that is basically passing through the solid. We said vibrations or sound passes through solids quicker. True? So this is the reason why you hear the vibration faster, okay? But the sound that is in the air, obviously, you're going to hear later, or there is a lag. That is because sound travels slower in the air. So to revise this real quick, this happens because sound travels slower in air compared to in solids. And that's the end for this session. I'll say keep an eye on these video lessons. Make sure you revise them, and I'll see you next time. Assalamu alaikum wa rahmatullah.